We used to judge computers by a simple number, how fast the needle was spinning. Raw clock speed was the undisputed king of performance. 2026 marks a definitive turning point, with Intel and AMD adopting hybrid core splits and Windows finally solving the ARM software gap through Prism emulation. The era of the one-size-fits-all processor has ended. To navigate this shift, you have to look closely at the central processing unit, the core brain of your device, an intricate grid of transistors etched into silicon, processing billions of microscopic instructions every second. These internal pipelines process data in radically different ways. Today, evaluating a personal laptop or a global enterprise network requires a precise audit of the underlying silicon architecture. This animated schematic shows the von Neumann architecture, the basic foundation of most processors. It physically separates system memory from the CPU itself. Inside the chip, the control unit acts as the manager, parsing instructions. The arithmetic logic unit acts as the worker, doing the actual math. And internal registers serve as ultra-high-speed temporary storage. Watch this continuous loop. This is the fetch, decode, execute cycle, happening billions of times a second. Data flows in, the manager dictates the task, the worker crunches the numbers, and the result is stored. This exact operational rhythm powers almost every device on Earth. But the underlying language commanding that rhythm has fractured into two fiercely opposed camps, x86 and ARM. For decades, this split forced a zero-sum choice upon the industry. You either prioritized raw computational power, or you optimized for absolute battery efficiency. The x86 architecture, driven by Intel and AMD, conquered computing environments where thermal limits and battery constraints do not exist. This visual represents complex instruction set computing, or CISC. x86 relies on this model to tackle massive, complicated instructions as heavy single blocks. This brute force processing generates the massive data pipelines required for professional 3D rendering and modern AAA gaming. Because x86 has dominated the traditional desktop market for 30 years, thousands of proprietary corporate enterprise applications are hard-coded to communicate exclusively in this language. But x86 carries a severe physical penalty. The moment you disconnect from the wall, the chip must aggressively throttle its own processing, often dropping 30 to 50% of its power just to keep the battery alive. If you are building a stationary workstation for heavy visual throughput, x86 is the required tool. But the second you rely on a battery, that heavy computing footprint becomes a liability. ARM took the opposite path. Rather than digesting massive code blocks, it uses reduced instruction set computing, RISC, breaking tasks down into incredibly lean, highly efficient pieces. By managing power at a microscopic level, ARM allows mobile professionals to maintain full rendering and processing speeds entirely on battery power, without triggering severe thermal throttling. This split comparison chart tracks ARM's violent expansion into enterprise data centers. Compared to the massive heat output of x86 servers on the left, cloud providers like AWS and Google are utilizing the minimal footprint of ARM instances to process web services at 40% higher energy efficiency. And when the chart shifts to ARM's internal layout, you see unified memory. By allowing processing components to share a single memory pool without strict hardware bottlenecks, ARM delivers the massive data bandwidth required for complex artificial intelligence inference tasks. By prioritizing strict thermal control, ARM evolved from a simple, low-power phone processor into the critical infrastructure supporting global cloud computing. The absolute borders between power and efficiency dissolved in 2026. Market pressures forced both camps to adopt their rivals' core strategies to remain viable. To stop battery drain, x86 completely restructured its silicon layouts. It dynamically routes heavy workloads to high-power performance lanes and background applications to ultra-efficient cores. Simultaneously, ARM solved compatibility. Using Prism emulation, ARM translates legacy x86 code with native performance. This convergence has forced fundamentally opposed architectures to merge into hybrid models, effectively erasing the old battle lines of the Silicon War. Arguing whether Intel chips, AMD desktop processors, or Apple silicon is universally superior misses how the modern industry actually operates. Effective hardware evaluation centers on specific real-world workflows. Architectural alignment has replaced raw clock speed as the primary purchasing metric. We operate in a highly specialized ecosystem. The microscopic design of a gold trace immediately dictates the operational capabilities of massive global data networks. The ultimate power in modern computing comes from matching the specialized microscopic architecture directly to the macroscopic task.